Hi everyone, this is Ihab Mohammed, a PhD student at Indiana University. In fact, autonomous navigation in unknown cluttered environments with limited sensing capabilities is a challenging task due to the uncertainty and complexity of such environments. One of the most commonly used control strategies is model predictive control. However, global guidance is required in order to ensure effective navigation, especially when facing challenging environmental conditions or navigating beyond the planning horizon, as you can see in those videos. In general, these global guidance can be achieved by integrating the local planner with motion planning algorithms or data-driven approaches in order to identify visible paths that guide the local planner toward its desired goal. Instead, we propose GEP MPPI, which is an online learning-based control strategy that integrates the MPPI algorithm with a local perception model based on sparse Gaussian process. The key idea here is to utilize the learning capabilities of SGP to construct a variance surface, which allows the robot to learn about its surrounding navigable space, then identify the recommended sub-goals, and finally recommend the optimal sub-goal for the local planner. Then MPPI computes the optimal control sequence that satisfies both robot and the collision avoidance constraints. Such a proposed approach eliminates the need for the global map or the offline training phase as in RL techniques, while escaping the risk of being trapped in local minima, leading the robot to navigate in complex environments. The first component of our proposed approach is MPPI, which is a sampling-based empathy method that can be applied to nonlinear dynamics and the non-convex cost functions. The key idea here is to sample thousands of trajectories in real time from the system dynamics. Then, each trajectory is evaluated according to a predefined cost function, where all trajectories are executed individually in parallel using a GPU. After that, the optimal control sequence can be updated over all trajectories. The second component is the GP sub-goal recommender policy. Here we present a concrete example of SGP occupancy model applied to our Jackal robot with an onboard 16-beam velodyne lidar sensor and located in an unknown cluttered environment. First, we generate the occupancy surface by projecting the raw points clouds on a 2D circular surface around the robot. Then we use the SGP to model the probability of occupancy. The variance surface shown in the last figure indicates the uncertainty associated with the predicted occupancy, where black areas are occupied while the white ones are free spaces. Finally, we define the centers of local free spaces as GP frontiers, which serve as local recommended subgoals to our controller. In this work, we introduced two operating modes for the GP MPPI algorithm called the simple and recovery modes. In the simple mode, MPPI always follows the optimal sub-goal recommended by GP. In contrast, in the recovery mode, MPPI follows the recommended sub-goal only when the robot is at risk of being trapped in local minima. In this video, we present the simulation results of our proposed control strategy in maze-like environment considering the two operating modes. We can clearly observe that our proposed approach successfully achieves collision-free navigation in both modes without getting stuck in local minimum. Moreover, activating the recovery mode improves the average distance traveled by the robot. We can also observe that the assistance provided by GP to MPPI to overcome dead ends when the recovery mode is utilized is more than 42%. We also experimentally demonstrate the applicability of our proposed control strategy in a complex unknown L-shaped corridor environment. We can conclude that both operating modes ensure collision-free navigation with an average linear velocity of 0.8 meters per second, without the risk of being trapped in local minimum while moving towards their desired state. However, the two baselines failed to complete the control mission due to the challenging environmental conditions. So please scan the QR codes for watching the entire results and forking our GitHub repository. Also, please feel free to shoot us an email if you have any doubts or looking for collaboration. Thank you for watching.